now going to look at the problem of calculating the distance on the Earth between any two points at the same latitude, but not necessarily at the equator. We have come across calculation of Earth distances before. The great circle distance between any two points on the Earth can be calculated using a general equation involving spherical trigonometry, but this is beyond the scope of the syllabus. Consequently, problems involving the calculation of great circle distances are limited to those where the 2 points lie on special great circles. These are when the points are both on the same meridian, or when they are both on the equator. Suppose we have a chart like this with a route on it. We measure the track distance with a pair of dividers. If there is no graduated scale line at the bottom of the chart, we can measure against the number of minutes of change of latitude. Can we do the same thing against the change of longitude? The answer is no, of course. 1 minute of change of longitude is not 1 nautical mile, except at the equator. Let's see why. We'll go back to some basic concepts. All meridians, along with their associated antimeridians, are great circles. However, only one parallel of latitude is, which is the equator. All other parallels of latitude are small circles. 1 nautical mile equals 1 minute on any great circle, for instance, on a meridian or at the equator. Therefore, at any latitude, 1 minute of change of latitude always equals 1 nautical mile. However, this is true only for change of latitude, or at the equator for a change in longitude. So now let's define departure and work out how to calculate it. Departure is defined as the distance between two meridians along a specified parallel of latitude. So departure is always a rhumb line, the parallel of latitude. It's important to understand this. There will also be a great circle distance between 2 points, which will be shorter, but this is not departure. It's also possible to calculate either the rhumb line or the great circle distance between 2 points not at the same latitude, but these are not departure either. It has to be along the parallel of latitude to meet the definition. It's usually measured in nautical miles, but it could be in kilometres. Departure will always be greatest at the equator, where it is part of the great circle. It reduces as the meridians converge, and becomes 0 at the pole, where all meridians meet. At the equator, the change of longitude in minutes is multiplied by 1. At the pole, the change of longitude in minutes is multiplied by 0. Departure is therefore a function of cosine, which has a value of 1 at 0 degrees and 0 at 90 degrees. The equation is therefore that departure equals the change of longitude in minutes multiplied by the cosine of the latitude. In the same way that we examined the sine curve when looking at convergency, let's look at some of the more common values of cosines of angles, because these frequently come up in questions on general navigation. Here is a cosine curve. Let's look at the angles between 0 and 90 degrees. The cosine of 0 degrees is 1. The cosine of 30 degrees is 0.866. The cosine of 45 degrees is 0.7071. The cosine of 60 degrees is a half, or 0.5. The cosine of 75 degrees is about a quarter, or more accurately, 0.259. And the cosine of 90 is 0. Cosine reduces from 1 to 0 as the angle increases between 0 and 90 degrees. The relationship between departure and change of longitude is therefore defined by the cosine of the latitude. This gives us the basic departure formula. Departure equals the change of longitude in minutes multiplied by the cosine of the latitude. Consider two meridians on the Earth, joined by a parallel of latitude. We can extract the basic elements of this situation in the sketch. In this example, the change of longitude is 20 degrees. Multiply by 60 to convert it into minutes, then multiply by the cosine of 52 degrees. This gives a departure of 738.8 nautical miles. Test questions are unlikely to be as simple as that. They usually involve conversion of units from kilometres to nautical miles, or some rearrangement of the equation. Take this example. An aircraft at position 60 north and 5 degrees and 22 minutes west flies 165 kilometres due east. What's the new position? Firstly, convert 165 kilometres to nautical miles. To do this, divide 165 kilometres by 1.852. The answer is 89 nautical miles. Now we need to substitute into the departure formula. So, departure equals the change of longitude in minutes multiplied by the cosine of the latitude. Which of these do you know? The departure is 89 nautical miles. Substitute it into the equation. The latitude is 60 north. Its cosine is a half. Rearrange the equation. This gives 178 minutes of change of longitude. This is 2 degrees and 58 minutes from an initial longitude of 5 degrees and 22 minutes west. So, since we are going eastwards, it is 5 degrees 22 minutes west minus 2 degrees 58 minutes, which equals a new longitude of 002 degrees 24 minutes west. The new position is 60 north and 2 degrees and 24 minutes west. Here is another example of a different substitution. In this one you are given the departure and have to find the latitude instead. In which latitude is a difference of 44 degrees and 11 minutes, equivalent to a departure of 2,000 nautical miles. As usual, start with the formula. Departure equals the change of longitude in minutes multiplied by the cosine of the latitude. Which of these do you know? You know the departure and the change in longitude. Write them in. We now need to convert 44 degrees and 11 minutes into minutes. It comes to 2,651 minutes. Now rearrange the equation to make the cosine of the latitude the subject. Use the arc cosine function on your calculator to solve for the cosine, which gives us a latitude of 41 degrees. So the latitude is 41 degrees. Remember, it could be north or south. Convergency and departure are symmetrical either side of the equator. You need to be able to solve questions where you are given departure at one latitude and have to solve it for another. Consider this question. An aircraft leaves position G at latitude 40 south and flies the following rhumb line tracks and distances G to H, track 180 true, distance 240 nautical miles. H to J, track 270 true, distance 240 nautical miles. J to K, track 000 true, distance 240 nautical miles. What is the rhumb line bearing and distance from K to G? There are two ways you can solve these types of questions. One is by a double substitution into the basic departure formula. It works, but it's slower. The other is by use of the following formula. Departure at latitude A divided by departure at latitude B equals cosine A over cosine B. The new formula is quicker. Let's do the question both ways. Firstly, by using a double substitution into the basic departure formula, and then secondly, by using the new method. You should then see the advantage of the new formula. Let's look at the double substitution method first. We can't directly find the departure or distance between K and G because, whilst we know the latitude, we don't know the change of longitude. However, if we can find the change of longitude between H and J, which we can calculate, this will be the same as the change of longitude between K and G. We need the departure and the latitude between H and J. We have the departure. It's 240 miles. But we first need to find the latitude of H. 240 nautical miles down a meridian equates to a change of latitude of 4 degrees. It's simply 240 divided by 60. So H is at latitude 44 south. Our method will now be to find the change of longitude from H to J from the departure. This will be the same change of longitude as from K to G. Once we know the change of longitude from K to G, we can find the departure at 40 south. Write the departure formula down for the 44 south situation. Departure equals the change of longitude in minutes multiplied by the cosine of the latitude. Which of these do you know? The latitude is 44 south, and the departure is 240 nautical miles. Rearrange to make the change of longitude the subject of the equation, and solve to get the change of longitude from H to J as 333.6 minutes. This is also the departure between K and G. They're the same two meridians. Now we're able to solve the departure equation at 40 south. The latitude is 40 south, and the change of longitude is 333.6 minutes. This comes to 255.6 nautical miles. And the rhumb line bearing is obviously 270. It's a parallel of latitude. Now let's look at the method using the new formula. We start with the same diagram. The formula is departure at latitude A divided by departure at latitude B equals cosine A over cosine B. Let's rearrange it to make the unknown departure, which we'll call departure at latitude A, the subject of the equation. Choose latitude B to be the one for which you already know the departure, 240 nautical miles in this case, which is 44 south. This means that you can solve for latitude A, which is 40 south, without any further rearrangement of the formula. It now becomes departure at latitude A equals departure at latitude B times cosine A over cosine B. The departure at latitude B is 240 nautical miles. Cosine A is the cosine of 40 degrees, and cosine B is the cosine of 44 degrees. Multiply that out on a calculator and the answer comes to 255.6 nautical miles, which is the same as our previous answer, but a lot quicker to work out. Don't forget that, for some questions, it is not always necessary to calculate. There will always be 4 optional answers given, and it may be possible to solve the question by elimination of the impossible answers and save calculation time. Take this question. An aircraft at position 27 north and 170 degrees west travels 3,000 kilometers on a track of 180 true. Then 3,000 kilometers on a track of 090 true. Then 3,000 kilometers on a track of 000 true. Then 3,000 kilometers on a track of 270 true. What is the final position? The answer options are A. 27 north, 170 west. B. The equator at 170 west. C. 27 north, 173 degrees 18 minutes west. Or D. 27 north, 143 degrees west. Now there are 3 ways you could approach this question. You could calculate every step, or you might see that the numbers chosen have been designed to allow you to take a shortcut, or, best of all, you might see at a glance that only one answer can possibly be right. Tick the correct box and go to the next question. Let's start with the full calculation. We are at 27 north and we fly 3,000 kilometers south. We need to know the new latitude, so we need to convert kilometers to nautical miles and work out the change of latitude. So we need to divide by 1.852, which gives us 1,619.87 nautical miles. For all practical purposes, we can treat this as 1,620. Divide 1,620 by 60 to get the number of degrees, and we find it comes to 27 degrees. We are at the equator on the same longitude. This makes the calculation of departure along the easterly track easy. It's also 27 degrees. Flying eastwards from 170 west gives us a longitude of 143 degrees west. We now fly another 27 degrees north to put us at 27 north again, this time at a longitude of 143 degrees west. Now we need to fly 1,620 nautical miles westwards. We have to convert this to departure. As always, substitute in what you know. In this case, it's the departure, 1,620 nautical miles, and the latitude, 27 degrees. Rearrange in the usual way to give 1,818.17 minutes of change of longitude. We need to convert this to degrees and minutes in order to be able to use it, so divide by 60 to get 30 degrees and 18 minutes. We are at 27 north and 143 degrees west. So flying 30 degrees and 18 minutes further west will put us, still at 27 north, at a longitude of 173 degrees and 18 minutes. This was answer C, but it has taken a fair bit of calculation to get there. There was a numerical shortcut which would have saved time. The clue came with the information that the leg distance was 3,000 kilometers. If you think back to the early part of the course, you should remember that the circumference of the Earth is 40,000 kilometers, and that 10,000 kilometers is 90 degrees change of latitude straight up a meridian. So 3,000 kilometers will be 3/10 of 90 degrees, which is 27 degrees of change of longitude. The examiner chose that latitude and distance for a purpose. It was to place part of the calculation at the equator to keep it simple. If you had seen that link, you would have saved time. The syllabus often requires you to draw on work from earlier parts of the course. However, the easiest way to have done this particular question would have been to be able to visualize what is going on and instantly eliminate the impossible answers. We start in the Northern Hemisphere and fly 3,000 kilometers south. We don't need to work out the exact latitude, it's just further south and therefore nearer the equator. If we then fly east, then north, then west, and if we fly the same ground distance east and west, the change of longitude when flying westward at the higher latitude will be greater than when flying eastwards at the lower latitude. Therefore, the aircraft will finish up at the same latitude but further west. Answer C is the only one which fits. A is the start position, eliminate it. B is on the equator, eliminate it. And D is out to the east of the start position, not west, eliminate it. That's a lot quicker than all that calculation. Don't overlook the simple solution sometimes. But you do need to be able to see the big picture. A diagram, even a rough one, nearly always helps. Let's summarize what we have done. The basic departure formula is departure equals the change of longitude in minutes multiplied by the cosine of the latitude. It's unlikely that the question will be asked in such a simple form. So, expect unit conversions and rearrangements of the equation.